these calculus of these parametric functions. So let's just review. What's the idea of a parametric function? What's the idea behind it? So for instance, here's a parametric function. This isn't the way you normally write them like on your paper, but this is the math line on GC. What's the idea behind a geometric or a parametric function? What's the idea behind it? Nick knows. So describing or understanding a function is always about what's the independent thing and what's the dependent thing. That's what always, if you're asked to describe or understand a function, it's really about what's independent and what's dependent, right? And then that's really what it defines the function. So with a parametric function, what's our independent thing? Yes, sir. Independent is x and y. Agree with that? Neil, you raise your hand. Parameter is independent. Which is it? T, the parameter, right? The parameter t. And does that get graphed? Does that have an axis? No. So normally, what we're used to was we graph dependent on the vertical axis as a function of independent on the x-axis, but now our independent thing is kind of this thing that's changing behind the scenes. It's not in the graph. So what's the dependent thing then in this function? Nick knows. Neil knows. Saying 3. What's the dependent thing in a parametric function? Lee? X and Y, right? Ordered pairs. So now we've got this parameter changing, and as the parameter changes, it's spitting out or giving corresponding values of ordered pairs, right? Okay, so that's just a review. So I want you to work on these first 3 questions. This is a handout that there's been lots of technology issues today, and I couldn't actually print your handouts. So you don't have to write it down word for word. You want to have good notes, but it might take too long to write everything down word for word. But I want you to work on these first 3 questions relative to that function and this part of the graph. So this is the x-axis here. We got negative 20, negative 19, negative 17 here, and then negative 15, negative 14, negative 11, negative 12. Let's see. Again. So x-axis, y-axis. It just doesn't, you're not showing the origin, right? We're down here in the 4th quadrant, okay? This is the point, negative 17, negative 12. It's that point right there. Okay, so work on these first 3. Don't spin your wheels. So get right to thinking about it, working on it. You're either making progress or you're talking to somebody, okay? You're either making progress or talking to somebody. These first 3 questions. Couple minutes, go. Okay, so I put the answer to number 1 up there. That's pretty straightforward. The value of the ordered pair is just what you get at t equals negative 2. So you get negative 19, negative 14. All right, dx dt. Jordan, did you get dx dt? And then did you put negative 2 in that? Okay, so then at negative 2, what does dx dt equal? Is it positive 24? Someone get that? Is that right? Okay, so we get 24. What does that mean? What does positive 24 mean for dx dt? Second, tell me your name again. Yeah.
Oh, me?
Yeah.
Zach.
Zach. What does 24 mean for dx dt?
I was going to say that the instantaneous rate of change of x with respect to t is 24.
And what does that mean? Yes, exactly.
So for very small values, or I guess any value of x, or any value of t, any change in t times 24 is what's going to give you x.
Right. Given any change in t. Any change in t?
Or no, just at that point.
Yeah. So for a small, so now we've got a changing rate, right? For different values of t, the rate changes. So this only works now. We can only make these conclusions about the rate just for a very small moment around where t equals -2. So close to t equals -2, given any small change in t, what can we say? Then we can determine the change in x. And what's the change in x? 24 times as much as that change in t. Here we are again, right? Rate of change. What does this mean? It means that given a small change in t, we know how much x changes relative to that change in t. 24 times as much. So tell me about that. How is x changing? How is x changing if the rate of change is 24? Increasing or decreasing? Increasing because it's positive. How is it increasing? Fast, right? Rapidly. Compared to like a rate of change of 1 or 2, this is a really, really high rate of change. For a small change in t, x is shooting up compared to t, right? So x is changing rapidly compared to t. High rate of change, right? High rate of change. Makes sense. Okay, so now orientation of the curve. So given that the rate of change is positive 24, how are the points being generated? So what does the 24 tell us about how points are being generated? As t changes, what's increasing in magnitude?
The
X value, right? So this, because that rate is positive, x values increase, right? Therefore, are we generating points up and to the right or down and to the left? Yeah, for change in t, we're generating point, x is increasing. That means we have to be generating points this way. Whatever way corresponds to left to right, right? Left to right would have to be then this way. That's left to right because x is increasing for increasing t. Does that make sense? Any questions? Okay, moving on. All right, so here's 4, 5, and 6. I gotta show you the graph still. So you use the graph to make a prediction for dy dx at t equals -2. So do 4 through 6. Okay, work on. I'll have to read them to you. Work on 4 through 6. Go. Again, this is the point. -17, -12. Right here. So now, again, dy dx, okay, dy dx. Okay, a couple minutes, work on these. I just want to focus on 4 and 5. So if you can get 4 and 5, then 6 is past exercise. We don't have to do that. So how do we do on number 4? How can we predict what dy dx is? Somebody new? Be able to predict dy dx? Basil?
Can you take the derivative of the y part or predict? I guess you can
So the prediction would just strictly from the information on the graph.
then you can just take the rate of change.
Yeah, and how do you do that? That's
You could just use 2 points
okay.
and then just evaluate the slope.
How
So
about this point? Yeah.
the top and the point.
And so what is it?
That's
Positive for sure.
I think.
So these are each 1. These are all units of 1.
Okay, so then just 2.
Yeah, so about pretty close to 2,
Yeah.
right? For a change of x of 1, y increases by 2. Or what? dy equals about 2 dx, right? Changes in y are about twice the change in x. And that's our rate of change of y with respect to x. So about so this is about 2. Okay? And now we want to get it exactly. So I want to get it exactly. I want to get dy dx. So one thing is, how about can we get y as a function of x? So we did that in the last class, or we've been doing it. We're combine the equations, get rid of the t, and just get an equation of x and y. How about here? How's that looking? It's not going to be great, right? So we got x is t cubed. This is a quartic polynomial. This is a cubic polynomial. Even a cubic polynomial. So t equals something with x's. Is that going to be easy to do? Is it going to be possible? It's not even going to be not even possible to do. Okay? So this idea of solving t in terms of x and then plugging it in this case, soon I'm going to show you the whole graph of this, and you'll see very quickly why this is not going to be like possible. Okay, so we're stuck with our x as a function of t and y as a function of t, and we can't really get y and x in an equation together, meaning we can't get y as a function of x and then do an old school first calculus derivative. Okay? So somehow else I want to try to get what dy dx is. Anyone have an idea? Yes, sir. Yeah. Okay. Sorry, go ahead. Is this legitimate? Can you do this? Well, think about this. If you think about the way that we're saying what dy equals, the rate, I'll call m sub y dt, and dx equals m sub x dt is the rate with respect to x. So for the same change in t, we're going to get some change in y and some change in x, right? And if you divided those, that'd be the rate of change of y with respect to x, right? So this is totally legitimate, right? For the same change in t, we'll get the change in y and the change in x. The ratio of those will be our rate of change. Okay, so what is dy dt? 6t minus 1 all over. And so then at t equals negative 2, I think if you do the math, you get 17/8. Is that right? And how was our prediction? Yeah, that's just a little 17/8 is a little bit more than 2, right? Just like it's 2 and an 8. Okay, so our prediction was good, but this is exactly your out now, dy dx. Okay, so the equation of the tangent line would just simply be what you've done in the past. Got the point, negative 17/12, and the slope is the rate of change, 17/8. So I'll leave that as an exercise for you. You can brush up if you've forgotten how to do that, but you've done that many times in the past. Okay, any questions on these first 6 questions of the activity? We're good? All right, so now I'm gonna show you the rest of the graph and show you how this idea of making y as a function of x is not easy or maybe even possible. So here it is, GC, a little bit here. Zoom out. So is y a function of x? No. So it's kind of no wonder that we can't write y. We can't easily get y equals something, a simple equation with x's in it. Y is clearly not a function of x. Is x a function of y? Neither is x a function of y. But is this a graph of a function? Parametric function, right? For every value of t, you get one ordered pair. So that's a perfectly legitimate function, right? For every value of t, you get an ordered pair x and y. Okay, so the next thing we'll talk about is, I'm interested in this very highest point here. So somewhere here is the highest point. Okay, so I want to figure out what that is. What's going on there mathematically that can help me figure out what the highest point is? And so we want to think parametrically now, right? So for a change in t, what's happening as t changes at that highest point? As t changes, right? Because we're thinking about this in terms of parametric function. As t changes, what's true in the tiny moments around that highest point? Yeah, Chris. Right. So at the very highest point, there's no change in y. Right? So dt would indicate that dy is 0. Therefore, dy dt is, for change in t, we have 0 change in y. So that's the mathematical kind of key to figuring out what point this is. So what was our dy dt? Negative 8t cubed plus 6t minus 1. And that equals 0. Now that's a cubic. That doesn't factor nicely. It doesn't give nice rational roots. But I will tell you that there are 3 zeros to that. So 3 values of t that make that 0. And one of those will give us the highest point. So let's find out what that is. Looks like t is negative 0.955 about. And the ordered pair is negative 2.6 approximately and 6.03 approximately. So when t is negative 0.955, I get this ordered pair, negative 2.6, 6.03, and that's representing the highest point. Okay, but I told you that this equation actually gave 3 zeros. Why does it give more than 1? Do you see why it gives more than 1 0, not just the one at the top? Yeah, Logan. Does it give x-intercepts? So that'd be the x-intercepts of this graph. That's true. It'd be x-intercepts of the dy dt graph. But what would it be for this graph, or this function? Do you see where there's more places where dy dt is 0? Tell me, yeah. There's one right here, right? So right here on the bottom of the nose of this thing, there's another place where for a change in t, y doesn't change, right? You're going horizontally. And then still, last one. I think it's right there. So there's another place right there where for a change in t, y doesn't change, so your dy dt is 0. So that would be the three t values that you get would give you those 3 points. Okay, so back to the sheet. Any questions on that? What we just talked about there. Okay, here we go. So back to the sheet here. So now I want you to, same parametric curve. I'll pull the curve up. There's a rightmost point. And this you can do with algebra without a calculator and without anything fancy. So the rightmost point on the curve, I want you to find the rightmost point of this curve?
You just try one of one, you make one. From 0 to 13, you just get that constant.
Okay, Rand, did you get this? So mathematically, what are we looking at here to figure this out? The rightmost point. What about it? Okay, so what was true about dx dt at this rightmost point? Is it 0? That would be saying that for a change in t, x wouldn't change. Is that true? The rightmost point? Yeah, like for a change in t, it's like it's heading vertically, right? So at that one moment, at the rightmost point. Let me zoom in on that. Be easier to see if you're closer. So we're right there. So at that one moment where dx dt is 0 for a change in t, there's no horizontal change in the points. It's all vertical change. All right, so keep going. How'd you do? So what'd you get? Okay, what is it? So 3t squared minus 6t. You can factor that into 3t times t minus 2. And we got t equals 0 and t equals 2. Okay, so now we got 2 again. So which one is it? How do we know? Yeah, so since we have the graph already, we can see that it's at this point 1, 4. So we can plug in t and confirm which one gives us the point 1, comma 4, and that is t equals 0. So when t equals 0, we get the point 1, 4, and that's the rightmost point. It's for just a moment there, it's all vertical, right? It's all vertical. We're just right close to t equals, or just at t equals 0. Okay, so what about this t equals 2? Where is that? So is that going to be back over here on the head of the anteater, or down here under the neck? Yeah, so we know the increasing t is this way. So t equals 0 is going to be further down here. So let's see what's happening. Oh, other way. So can you see here that? Zoom out one more time. No, just trying to zoom out. What's going on? Oh, because it's still on this thing. There we go. So there, you can see it now. Right around here. As I say, t equals what? 2? There it is, right there. There it is. So there's another place that we didn't see before because I wasn't showing you that part of the graph. But at t equals 2, again, all the change is y change, no x change. That's why dx dt equals 0 at that t equals 2. And that's at -3, 18. So that's like a local left point, right? It's not the leftmost point of the whole graph because we have all those points over there. But in the local area, it's like a local left point. Okay, very good. So let's move on here. Any questions? So did you get -1, 4, first of all? So at t equals 1, you should have gotten -1, 4 for the point. Now we want to predict dx dt, dy dt, dy dx, and the second derivative with respect to x. Okay, so in order to do that, so our very first point was t equals -2. That was down here. Somewhere down here was t equals -2. So that's important because you need to know which way the points are being swept out in this curve as t increases in order to make these predictions. So what about dx dt? Dx dt. Positive, negative, or 0? People are saying negative. Why negative? For a change in t, x is decreasing through here, right? Because we're moving, because the curve is being swept out this way. See that? So for a change in t, x is decreasing. We're going right-ish, right? Right-ish. Therefore, dx dt less than 0. What about dy dt? Less than, equal to, greater than 0. Also less than, because as t is increasing, are we going up-ish or down-ish? Down-ish, right? Down-ish, right? So that means that for changes in t, y is decreasing. So the dy dt is less than 0. What about dy dx? Two ways to think about this. Dy dx. Positive or negative? So what's one reason you can see that dy dx is positive? Dylan, yeah.
I know that if you divide a negative by a negative,
Yeah, that's valid, right? We show that dy dt is negative, dx dt is negative, divide, you get a positive. Okay, what's another way to see that dy dx? Yes, sir? Yeah, so for a change in x, right? Change in x, y goes up. We're heading up to the right for a change in x. So t is out of the question here, right? T is not in the picture. It's just how does y change with a change in x? And that would be up and to the right. Sorry, up as you go right. Okay. What about the second derivative? Remember this from Calc 1? The second derivative. Okay, y negative. Concave down. What does that mean? It means now we're asking, what does the rate of change do for increasing x, right? So really this derivative is, what is the derivative of the first derivative with respect to x? Meaning for a change in x, how does the derivative change? So over here, they're positive dy dx. So dy dx is positive, but it's becoming more positive or less positive? So you see this becoming less positive as x increases. So the derivative is decreasing, becoming less positive. That's what makes the concave down shape. Therefore, less than 0. Questions on those four? So it moves left. That means dx dt is 0. It moves down. That means dy dt is 0. Y increases for an increase in x. So dy dx is positive. But that rate is decreasing, getting less positive. So the rate of the rate is negative. Okay, so we saw what dy dx is. What was dy dx again? The ratio of those two derivatives. Let's write that out. So what was it? Negative 8t cubed minus plus 6t minus 1 over 3t squared minus 6t. And how did we get that? I got that by what are we doing? We're taking the derivative of y. See that? So that's the derivative of y. So I want what? Dy dt over, so the derivative of this, but I want it with respect to x. So then I need dx dt, right? So this is the exact same thing as this. Watch. I'm going to take the derivative of this with respect to t. That's what I did here, right? I took the derivative of that thing in parentheses with respect to t. So what's that? Dy dx. D dy dx with respect to t, but then that's with respect to t. I need it with respect to x, so divide by dx dt again. So getting the second derivative with respect to x is the same pattern as getting the first derivative with respect to x. I take the derivative of what's in parentheses with respect to t, but then I need it with respect to x, so I divide by dx dt. Same thing, I want the derivative of this with respect to x, so I take it with respect to t, but then I need it in respect to x, so I do dx dt. Did you follow that? So getting this dy dt over dx dt is it's the same pattern you follow to get the second derivative with respect to x. So this says take the derivative of this with respect to t. How would I do that? How would I take the derivative of this with respect to t? Quotient rule, right? But then divided by another dx dt. So I do the quotient rule on that. That gives me the derivative of dy dx with respect to t. Then I divide by dx dt, and then that whole thing now is the second derivative with respect to x. And if I plugged in t equals 1, what would I expect? Negative, right? At t equals 1, we're expecting that thing to be less than 0 because we see concave down, or decreasing rate, right? Decreasing rate. Now, if you're trying to do a second derivative, make sure you simplify this all the way. That can save you a lot of hassle. Simplify this as much as you can. You might even be able to avoid quotient rule when you do that. Okay? Simplify that first derivative as much as you can before you start finding the second derivative. But in this case, that can't be simplified anymore. You have to use the quotient rule. And then if we plugged 1 into it, once we got it, we'd expect less than 0. 5 minutes? Okay. So remember when we talked about area and signed area? We said we wanted to use integral to talk about accumulation of area. So first of all, what region, given a function, this is f of x, what regions would integral help us find areas of, or signed area? The region, how is the region formed? Yeah, between the function and the x-axis, right? So we said if I took the integral from a to x, okay, and I was interested in what? Accumulating area, these areas of these regions between. So right now, what is my accumulated area? And then now, is it increasing or decreasing? Decreasing. Positive or negative right now? Almost 0, right? Maybe it's a little bit positive still, but about 0. And now what about, is increasing or decreasing? Positive or negative? Yeah, decreasing and negative, right? Because when you're below that x-axis, you have a negative contribution to signed area, right? And then we start increasing again. And somewhere over here, we're going to get back into positive territory. And then just keep increasing positive on that signed area, okay? So what was the rate of change of signed area? So how much is it growing by at any given value? Growing by that length right there, right? That's how much it's growing by, because that's where the area is growing. That's where it's accumulating. And so that rate is? The value of the function. Okay, I'm going to use u, because now we're using t for parametric functions, so I'm going to use u. So this was our signed area function, right? I'll call it capital F. So signed area. Remember this? And that accumulated what? It increased whenever the function was above the x-axis, and then it decreased whenever we're accumulating area below the x-axis. And so then actually to get area, we had to finagle this, right? So to get area, we had to do more work, right? But the integral itself just gives signed area. Increases and can be negative, can decrease according to where the function is. Okay, so when we do it with parametric functions, we're going to keep the same construct. We're going to still be thinking about areas between the curve and the x-axis. Okay, so we're going to use the same approach. in parametric functions. So it's still going to be the regions between the curve and the x-axis. Regions between the curve and the x-axis. So what we need to do then is we just need to transform this into t, right? So it's going to be the same structure transformed into the variable t. Okay. So our assigned area is going to be, so now our starting value is going to be t equals some starting value a. That's going to be a t value. Oh, sorry, it's going to be f of t then. So I didn't do it. So we want f of t now. And so we're going to be accumulating up to some value t. And so if you go back and look at this, what is f of u? Isn't f of u just y? Isn't that just y? Right? And then du is like dx, right? Changes in x. So that's what we're going to use. What is y in our, so if x is f of t, and y is g of t in our parametric function, then what is y? G of t. But now t is the independent variable. I need a different variable, right? So g of v, say. So that's the y value. That's the same as like f of u. And then what would dx be? Dx would be what? F prime of t, right? dy equals m dx, but now it's x and t. So dx equals the derivative, or the rate of change, times dt. So we're going to have f prime of v dv. So here's my y, the same as the f of u, and then here's my dx. So it's, again, same exact structure as this, so we're getting areas between the curve and the x-axis. But now now this is how you transform that into the variable t when you have a parametric function. X is a function of t, y is a other function of t. So you got the y dx. So we'll do like I'll show what happens with this, because some kind of strange things happen as we double back and go and head backwards in x. Okay, we'll start out Monday with that.